Hello, my name is Hans Burgerhoff and I work as a statistician in the UMCG. This video is part of a series of videos about medical statistics. In this video I would like to tell you something about the principles of a statistical test. Now, let us assume you work as a doctor and a researcher with children born after IVF. After seeing a lot of IVF offspring, you have the idea that these children might have higher systolic blood pressures than other children. Now let us assume that it's known that in a population of 4-year-old, naturally conceived children, the systolic blood pressure has a normal distribution with mean 96 mm mercury and standard deviation 6 mm mercury. Based on your own experience, in the population of 4-year-old children born from IVF, the mean systolic blood pressure would be larger than 96 mm mercury. To be 100% sure about this, we should take blood pressures of the total population of all 4-year-old children born from IVF, which is quite impossible to realize because our statement also includes future children. So we will take a representative random sample from the population of the present day, and based on the sample mean, we will draw a conclusion about the population mean. To formalize this idea, we formulate a research question. We think that the mean blood pressure, mu, in the population of 4-year-old children born from IVF is larger than 96 mm mercury. For statistical testing, this will be reformulated in a null hypothesis and an alternative hypothesis. The null hypothesis will play the role of the devil's advocate. In this case, the null hypothesis will state the mean is 96. The alternative hypothesis will reflect our research question and can be formulated in a one-sided way if we have good reasons to believe that the mean can be only on one side of 96. So, in this case, the alternative could be mu is larger than 96, or we can define the alternative in a two-sided way. The next step will be to collect data from the population we are interested in. We will calculate the sample mean and compare it to the hypothesized population mean. If we find a sample mean close to or even smaller than 96, there will be no reason to reject the null hypothesis. If we will find a very large value of the mean, the sample mean, then we will reject the null hypothesis. But how do we define much larger? For which values will we reject the null hypothesis? The scientific community has agreed on 5% risk of rejecting a null hypothesis, while in fact the null hypothesis is true. We call this the significance level of the test, and the symbol we use for it is alpha. The graph shows the sample distribution of the mean if the null hypothesis is true, with 5% of the right tail in red. This is the so-called rejection area. If we will find the sample mean in this red area, we will say the result is significant, and we will no longer believe the null hypothesis. So we will reject it. Here you see again the rejection area for the one-sided alternative. For the two-sided alternative, the rejection area is on both sides of the hypothesized mean. For both situations, we will reject the null hypothesis if the sample mean is in the rejection area. Another way of looking at testing is by means of a p-value. The p-value is defined as the probability of finding the sample result, or even more extreme, assuming the null hypothesis is true. So in fact, it's a conditional probability. In the PowerPoint, the one-sided p-value is shown as the blue area. The next slide shows the situation for the two-sided p-value. We use a two-sided p-value if we have a two-sided alternative. The two-sided p-value is the probability of finding the sample mean or even more distant from the hypothesized mean on either side, if the null hypothesis is true. If the p-value is smaller than or equal to our significance level, we will reject the null hypothesis and conclude that the mean systolic blood pressure in the population is significantly different from 96. If the p-value is larger than alpha, we cannot reject the null hypothesis, and this null hypothesis might be true. I will give two examples, both for testing a null hypothesis against a one-sided alternative. In the first example, we test the null hypothesis mu is 96 against the one-sided alternative the mu is larger than 96. We have from a normal distribution a random sample of 25 observations, with a sample mean 97.6, and the population standard deviation is known to be 6 mm mercury. What is the probability of finding a sample mean of 97.6 or more if in reality the null hypothesis is true? We will calculate this probability, the so-called p-value, by standardization. We subtract the hypothesized mean 96 from the observed sample mean and divide by the standard error. The standard error equals sigma divided by the square root of n. In this case, 6 divided by the square root of 25, which is 1.2. This will lead to a z value of 1.33. From table A1 in Kirkwood and Sterne, we find the probability 0.0918. We compare this p-value to our significance level alpha. Because 0.09 is larger than 0.05, we cannot reject the null hypothesis. We say we found a non-significant result. It's important to notice that we did not prove the null hypothesis. We simply have not enough evidence to reject it. The null hypothesis might be true. The p-value is larger than alpha. This is equivalent to the fact that the sample mean is not in the rejection area. In the second example, we test the same null hypothesis against the same one-sided alternative. But now the sample mean equals 99.8. Again, we calculate the p-value by standardization. This time, the p-value is 0.0008, much smaller than alpha. So now we will reject the null hypothesis. In this example, the difference between the observed sample mean and the hypothesized mean is that large that we no longer believe the null hypothesis to be true. We say we found a significant result. The sample mean is within the rejection region. When we perform a statistical test, only 4 situations can occur. In reality, the null hypothesis is true, or the null hypothesis is not true. For example, the null hypothesis states that the effect of a new treatment is equal to the effect of a standard treatment. The alternative hypothesis states that the effect of the new treatment is better. We perform a statistical test and we will draw a conclusion in the end. Either we will reject the null hypothesis or we will not reject the null hypothesis. This only gives 4 possible combinations as shown in the table. If in reality the null hypothesis is true and we will not reject it, we have a correct decision. If the null hypothesis is true, but we reject it, we make an error. We call this a type 1 error. We want to avoid making type 1 errors. We do not want to say the new treatment performs better than the standard treatment if in fact this is not true. We protect ourselves by taking the probability to commit a type 1 error to be small. This is our significance level, alpha. In most situations we will take alpha to be equal to 0.05. If, on the other hand, the null hypothesis is not true, the new treatment is really better than the standard treatment, we long to reject the null hypothesis. If we fail to reject it, we will make an error, a so-called type 2 error. The probability of making a type 2 error is called beta. The most important cell in this table, deciding correctly that the null hypothesis is not true, has a probability 1 minus beta, which is called the power. Be sure that your research always has a power larger than 80%. You can do so by including a sufficient number of respondents. I will tell you more about sample size calculations in another video. For short, the larger your sample, the higher the power. There's a lot of similarity between jurisdiction and statistical testing. The premises or starting point in jurisdiction is the accused is innocent. The starting point in statistics, the null hypothesis, is true. Then there will be a process of gathering information. In jurisdiction, reports are read, witnesses are heard. In statistical testing, data are collected, a p-value is calculated. Possible decisions in jurisdiction: if there is not enough evidence against the accused, the conclusion will be not guilty. If there is enough evidence, the conclusion will be guilty. In statistical testing, if the p-value is larger than alpha, we do not reject the null hypothesis. If p is smaller or equal to alpha, we have enough evidence to reject the null hypothesis. Please note that in both professions, type 1 and type 2 errors are made. There are a lot of statistical tests. Depending on your design, the number of groups you would like to compare, the nature of these groups, independent or matched, and the type of outcome variable, there will be a specific test to use. I will tell you more about these tests in videos to come. For now, make the exercises of video 5, check your answers. I wish you good luck. See you next time.